guys, welcome to Module 2 which covers vectors and geometry of space. So in this video, we'll talk about vector operations and specifically at the end of this lesson, you should be able to perform vector operations and interpret the results geometrically. Okay, what are the different vector operations? So by definition, let U be a vector with components U1, U2, and vector B with components B1, B2. And let C be a scalar. So the vector sum of these two vectors, U and B, is the vector of this form, which is read as U plus B is equal to U sub 1 plus B sub 1, which is the first component, and U sub 2 plus B sub 2 as the second component. Okay, the second operation is called the scalar multiplication, or scalar multiple of constant C with vector U is obtained by multiplying this vector U by the constant C. And this scalar multiple is obtained by multiplying each component of vector U by the constant C to get C U sub 1 as the first component, comma, and then C U sub 2 as the second component. Okay, the third operation is the negative of the vector B. So when you take the negative of vector B, we are multiplying each component of this vector B by negative, now to get negative B sub 1, comma, negative B sub 2. Okay, number 4, the difference of the two vectors U and B is obtained by subtracting U with vector B, and this can also be written as the sum of the vector U and the negative of vector B. So this difference is a vector with components U sub 1 minus B sub 1 as the first component, and U sub 2 minus B sub 2 as the second component. Okay, geometrically, the scalar multiple of a vector B and a scalar constant C is the vector that is absolute value of C times as long as vector B. So as you can see in this figure, if this is the original vector B, when you multiply this by constant 1/2, the length of the resulting vector is half the length of the original vector. And to get 2b, you multiply this vector b by 2, and geometrically this is twice as long as the given vector b. The negative of vector b is same length as vector b but opposite direction as b because this is negative. Same with negative 3 over 2 times b. This is negative. The constant is negative 1 and 1/2. Multiplied by this vector b. So this vector is negative is 1 and 1/2 length as the original vector but opposite direction because of the negative sign. So in general, we can say that if C is positive, then C times B has the same direction as the vector B. On the other hand, if C is negative, then C times B has the opposite direction. Okay, you can find the sum of the two vectors geometrically by first drawing the vector u in the Cartesian plane, and then at the tip of vector u, you draw the second vector b. Then connect the initial point of vector u with the terminal point of vector b to get the sum of the two vectors u and b. So as an example, given these two vectors v and w, and what we need to find are the following. Letter A, 1/2 of vector B. B is W minus B and C is B plus 2W. So to find the vector 1/2 B, just simply multiply this vector B by the constant 1/2. So we multiply each component of vector B by 1/2. So 1/2 of negative 2 is negative 1. 1/2 of 5 is 5 over 2. Okay, next in letter B, we need to subtract the vector W with vector B. And recall that the vector W is a vector with components 3, 4. B is a vector with components negative 2, 5. So To find the difference between these two vectors, we subtract their corresponding components, first to first, and then second to second component. So we have W1 minus B1, W2 minus B2. But W1 is 3, so 3 minus the first component of vector B, which is negative 2. So 3 minus negative 2, that's the first component. And then for the second component, 4 minus 5. So we have 3 minus negative 2 is 5, and 4 minus 5 is negative 1. So these are the components of the difference of the two vectors W and B. Okay, next we have the properties of vector operations. So in this theorem, let U, B, and W be vectors in the plane, and let C and D be scalars. So the first property is called the commutative property, wherein when you take the sum of the two vectors U plus B, this is also the same thing as the sum of vector B and vector U. Okay, the next property is called the associative property, wherein the order of the sum does not affect the value of the sum of the vectors. So when you take the sum first of the two vectors U and B and add it to W, this is also the same thing as the vector U plus added to the sum of the two vectors B and W. Next property is the additive identity property, wherein in the vector space, the zero vector is always the additive identity property, wherein any vector added to the identity uh, element or additive identity element, which is the zero vector, the sum is always the vector U. Next property is the additive inverse property, that for every vector U in the vector space, there exists always a negative vector U, that when added to vector U, the sum is the zero vector. So negative U is called the additive inverse element. Okay, next property is the um, associative scalar multiplication, wherein when the order of the product does not affect the value of the product of the scalars and the vector U. That is, when scalar C is multiplied to the scalar multiple of D and U, this is also the same thing as the product of the scalar C times D times the vector U. Okay, next property is called the distributive property, wherein if you're given two scalars um, that are added and multiplied by vector U, by applying the distributive property, we distribute U to each of these constant. So U times C or C times U, you get CU, plus D times U is DU. Another distributive property shows that if you're given two vectors that are added and multiplied by C, we distribute C to each of this vector to get C times U plus CB. And the last is any vector U multiplied by 1 is always equal to the vector U. And zero vector multiplied by any vector U is always equal to the zero vector. Okay, another theorem, 11.2. This is called length of a scalar multiple. So in this theorem, let B be a vector and C be a scalar. Then the magnitude of the scalar multiple C times B is also the same thing as the product of the absolute value of C times the length of the vector V. So absolute value of C here is the absolute value of the constant C. So this theorem 11.3 define the unit vector in the direction of vector B. So here, if B is a non-zero vector in the plane, then the vector U, which is defined as B over its length, is equal to 1 over the length of vector B times the vector B. So this vector U has length 1 and the same direction as vector B. So in this theorem, U here is called the unit vector in the direction of vector B. And the process of multiplying B by 1 over its length to get a unit vector is called normalization of vector B. Okay, so as an example, given these two vectors b and w, so we need to find the unit vector of each of the vectors b and w. So for the unit vectors in the same direction as vector b is defined as the vector over its length, or b over the length of vector b. But recall that vector b is a vector with components negative 2, 5. And to use this formula, we have to get the length of this vector b, which is equal to the sum of the square of each component. So the square of the first is negative 2 squared, square of the second component is 5 squared. But negative 2 squared is 4, plus 5 squared is 25. So 4 plus 25 is square root of 29. So the unit vector in the same direction as vector b is a vector with components negative 2 over square root of 29 and 5 over square root of 29. Or rationalizing the denominator, so we get negative 2 square root of 29 over 29 as the first component, and 5 square root of 29 over 29 as the second component. Okay, in letter B, given this vector W, and we need to find the unit vector in the same direction as vector W. Again, the formula is the vector over its length. Okay, but W is a vector with components 3, 4. The length is the square root of the square plus square of the first component plus the square of the second component. So 3 squared is 9, 4 squared is 16, and 9 plus 16 is 25. Square root of 25 is 5. So therefore, the unit vector in the same direction as vector W is a vector with components 3, 5, 4, 5. Okay, so in summary, the sum of the two vectors u and b is obtained by adding their respective components, u1 plus b1, u2 plus b2. And the second operation, which is the scalar multiplication of c and u, is obtained by multiplying each vector u by the constant c. So we have c times u1, c times u2. The third operation, which is the negative of vector b, is obtained by multiplying each vector of vector u by negative 1. So to get negative b sub 1 and negative b sub 2. The difference of the two vectors u and b is obtained by subtracting their respective components. So u1 minus b1, u2 minus b2.